All right, so this is Math 20-1, Unit 6, Trigonometry. And this is Mrs. Finley giving her a whirl. Okay, so we start this unit just with a little bit of review of trigonometry. First thing we're going to review is remembering our Pythagorean Theorem. A squared plus b squared is equal to c squared. This is a relationship that exists with a right angle triangle where the hypotenuse is c and the two sides of the right angle triangle, the two sides that are adjacent to the right angle, are a and b. So we can use this a lot. You're expected to know that and to know that that might be a tool that you're going to use to solve equations. We're also going to review our primary trig ratios. And we often use the mnemonic so, ka, toa to remember. Remember, if we're talking about an angle, so this is our right angle triangle, and that's what these primary trig ratios work with. The hypotenuse is always across from the right angle. The adjacent, so if we're looking from angle theta, the adjacent is right next to it. That's what adjacent means. And the opposite is across from that angle. So this would be our opposite. Now, of course, if we were looking from angle beta, the opposite and adjacent would switch because it's always, you have to think about which angle you're looking from. So talking about our three primary trig ratios, SOHCAHTOA means sine. So sine theta is equal to the opposite over the hypotenuse. Ka means cos theta is equal to the adjacent over the hypotenuse. And tan theta is the opposite over adjacent. Okay. We're also going to talk a bit about angles in standard position. So this is when we're looking at a rotational angle. If we think about our Cartesian plane, our x and y axis, as a thinking almost like a clock, where the origin is something that we can have an angle or a line that rotates around that origin. Then we have an angle in standard position. We have a few different things to talk about here. So we can talk about the fact that we have this here. If we have a point PXY, the line that connects to it is called the terminal arm. The angle that makes with the x-axis is called the rotational angle. And the angle the arm has with the x-axis is also called the reference angle. And we'll talk a lot about reference angles as we go on. And the x-axis, so this x-axis here is always the initial arm. Okay. Obviously, we're talking about angle theta. The length of that arm is called r, and the point would be at x, y. Okay. The terminal arm is the ray that is formed from the origin to the terminal point, P. The rotational angle is the angle formed when you start at the positive x-axis and rotate either clockwise or counterclockwise. Most of the time we're talking counterclockwise. If we go clockwise, we often will assign it a negative value for our degrees. The angle in standard position, the principal angle, is the positive rotational angle starting from the positive x-axis and rotating counterclockwise. So if it's rotated counterclockwise, it is positive. If we were to rotate it clockwise, it would be a negative. Okay? we're going to use this a lot, and we're going to use our primary trig ratios to talk a lot about what's going on. So we want to construct some understanding here. So this tells us to plot point 3, 4. So we just imagine if we're going to plot 3, 4, 3 and 4, so that would be this point here. Okay, we draw a line. You would use a nice ruler to draw that line. The length 2, 3, 4 is r. And if we were to make this into a right angle, we would see a couple of relationships that happen. We would see that this is 3, which is the x value of the point, and this is 4. Okay? This in here would be our theta. So we can, from this, determine a lot of information. So we've drawn the terminal arm that includes P, and we use point P to draw a right angle triangle and labeled the measures of the vertical and horizontal arms, which was the 3 and the 4. Now we want to calculate and label R, which is the radius. Well, what we have is a right angle triangle. So we're going to do that using our Pythagorean theorem. So using our Pythagorean theorem, R squared would be equal to 3 squared plus 4 squared. Right? So R squared equals 9 plus 16. R squared equals 25. So to figure R out, we take the square root of each side, and we get R is equal to 5. Okay? Now we want to write the 3 primary trig ratios of theta, the rotational angle. So again, we're looking from theta. And from theta, if we look at what we have, that means that our opposite is 4, our adjacent is 3, and our hypotenuse equals, well, we just figured it out, 5. So let's write those 3 trig ratios out using these. Okay? So using them, we have sine theta is equal to SOHCAHTOA, opposite over hypotenuse, which if we also look here, the opposite is the y value, and the hypotenuse is r, so that is 4 over 5. Cos theta, which is adjacent over hypotenuse, is the x value over r, right? Which is 3 over 5. And tan theta, oops, I forgot my theta there, is opposite over adjacent, so SOHCAHTOA. So opposite is our y value, adjacent is our x value. So that's going to be equal to 4 over 3. So we've figured out the 3 primary trig ratios from those. Now, in general, the trig ratios of angles in standard position are as follows. For any angle theta in standard position where the theta is between 0 and 360 degrees, with the terminal point PXY, the primary trig ratios are defined as, and this is a very important box, so maybe put a big star around it. Cos is always x over r, sine is always y over r, and tan is always y over x. Where r, this is the Pythagorean theorem, right? So where r is equal to the square root of x squared plus y squared. So they've just rewritten the Pythagorean theorem to express r. Therefore, we can take these and express x in terms of cos, x would be equal to r times cos theta, and that's just rearranging this formula, and y would be equal to r times sine theta. And we could write the point pxy as p is r cos theta, comma r sine theta. So this is another way that you could express those if you know that point, or if you know theta, right? And you know the length of the arm. Okay, so from that, we're going to do a little work. Determining the trig ratios given a point. So we've got those formulas that are there, that are in that magic box, right? I keep doing that, and I don't know why. Okay, so we've got these right here. We've got these. Sorry guys, my pen is not working. We've got these ratios to guide us. Okay, so we're going to use those to do this. The point P 4, 7 is on the terminal arm of an angle in standard position. Determine the distance r from the origin to P as an exact value. Well, from that magic box we have r is equal to the square root of x squared plus y squared. Well, we know that x is 4, so 4 squared plus 7 squared, which is y. So we just substitute that in. So r is going to be equal to the square root of 16 plus 49. So r is equal to the square root of 65. Now, we would look at that. Can we reduce that? Is there any factors we can take out of 65? I don't think there is, because 65 is 5 times 13. So that would be the lowest form for that radical. We can't reduce it. We can't change it to a mixed radical. So we have our value for r. Now, the next thing it wants us to do is determine the primary trig ratios of the theta. So let's think about what we know. We know that we now know r is equal to root 65. We know x is 4, and we know y is 7. So using those trig ratios of angles in standard position from our box that we saw up here, we can write out those 3 primary trig ratios. So let's do that. So from that box, cos theta is equal to x over r. So that's going to be 4 over root 65. Now, we don't like to have a radical in the denominator. Remember back when we did radicals, we rationalized the denominator. So we times the top and the bottom by root 65. And we get 4 root 65 over 65. Okay. Sine from our box is y over r. So that is 7 over root 65. And again, we have to rationalize the denominator. So we get 7 root 65 over 65. And then finally, tan theta from our little magic box is y over x. Well, y is 7 and x is 4. And we can leave it as a improper fraction for that ratio. Okay? Now, the next question on the next page says, determine the measure of theta to the nearest degree. Well, I always say use the ones that is closer to the information given. So because we got the point, tan is actually the one we probably should use. Just in case we made an error solving for r, we know that 7/4 is precise. So tan theta equals 7 over 4. So to figure out theta, that's going to be equal to tan negative 1 7/4, so that you have to use that button on your calculator. You use the second function and then the tan is to get the tan -1. When you put that in, you get 60 degrees. Now, check that so that you can make sure your calculator is in degrees, not radians. So if you put that in and you don't get 60 degrees, then that means that your calculator is on the wrong setting. Okay? And I get 60.25, blah, 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 blah. But if it was on radians, you would get a very different number. Radians would give you, sorry, let me just do it here. Second function, tan 7 divided by 4, it will give you 1.05. So you don't want to have it on that. And you can just get it to degrees using your mode button. Okay? Okay, alrighty. So that's a bit of review of how to find the angle. Okay? Think further. What is the relationship between the slope of the terminal arm and the trig ratios? Well, slope is change in y over change in x. Tan is equal to y over x. So the slope of the terminal arm is equal to tan theta. Interesting. So the slope of that terminal arm is 7/4. Okay? Just a little interesting extension there. Example number 2. If sine theta is 5/13, determine cos and tan in exact ratios. So thinking about this, sine is equal to, if you think about the box that we were referring to, sine is y over r, right? So that means that y equals 5 and r equals 13. We want to think about that in terms of our triangle, right? So if we draw our point here, okay, so we know that y is 5, right? We don't know what x is, and we know that r is 13, okay? So in this triangle, y is 5, and we don't know what x is. So we can use the Pythagorean theorem to figure out what x is, and that's what our first step is. So find x. Well, r squared is equal to y squared plus x squared. So r squared minus y squared is going to give us x squared. So let's substitute those in. So we're going to have 13 squared minus 5 squared is equal to x squared, right? 13 squared is 169 minus 5 squared, which is 25, equals x squared. So 169 minus 25, well, that conveniently equals 144, which is equal to x squared. So if I take the square root of both sides, 144, square root of 144 is 12. So 12 is equal to x. So I've got a lot of information there. Now, if I want to find cos and tan, I just have to substitute in my values for x, y, and r. Cos, oops, why did I write sos? Cos theta from our square. If we look at that, cos theta is x over r. So x is 12 and r is 13. And it says exact ratios, so we would leave it as a fraction. We would not change that because we're going to get a non-repeating decimal and it won't be an exact ratio. Tan theta, as we know, is equal to y over x. Y is 5 x is 12. So now we have cosine theta in exact ratios. So the first thing is determining what we don't know, which in this case was x, and then using that value to find our cos and our tan in exact ratios. And remember, exact ratios means that you can leave it in that fraction form. You should put it in lowest form. So if you happen to have gotten 6/12, you would reduce that to 1/2, but you can leave it in that fraction. Okay. If cos theta equals 2/√5, determine sine theta and tan theta in exact ratios. So again, we have to think about our ratios. Cos theta is x/r. Refer back to that box, right, which is 2√5. So that means x equals 2, r equals √5. So if we're looking at our terminal arm, we've written it here. I know that this would be 2, this would be √5, and we don't know what y is. So our first job is to use the Pythagorean theorem to determine what y is. So find y. Again, r squared equals y squared plus x squared. We know that we can subtract x squared here to get our y squared, right? Now we've got y by itself, so now we're going to substitute in to solve. So r squared is √5 squared minus x squared, which is 2 squared, which will equal y squared. √5 squared is just going to be 5. 2 squared is 4, which is equal to y squared. 5 minus 4 is 1, which is equal to y squared. We take the square root of both of these, and voila, y equals 1. Okay, so that's our first step. Now we're going to give the sine and tan in exact ratio. So sine theta, if you go back to that box, sine theta is y/r, which is equal to, now we know our y, which is 1/√5. Now, of course, we have to put it in proper form because we never will leave that radical on the bottom. So we're going to times the top and the bottom by √5, which would give us √5/5. Okay, so that would be my sine theta. Tan theta is equal to, and remembering this, it's equal to y/x. Y is 1, x is 2. So that would be our values for tan theta. So this is our answer for tan theta, and this is for sine theta. Don't forget to rationalize denominators, because if you don't, it's not in the right form. Okay.